Hello, Geography 231 students. Welcome to week 9, the first week post midterm. Let's see, a couple of housekeeping pieces here. I have started reading your papers. As I told you, I would give myself 2 weeks. I have 1 week left. Still got a few left to go, so working my way through those. And I am providing feedback and comments. So all you need to do is just basically access, turn it in the way that you submitted the file, and you should be able to see the paper there that you uploaded. And you'll just view it there, and you'll see in-text comments and specific feedback to questions, and if it looks like there's somewhere where I can help a student, point them in the right direction for finding data or thinking of methodological approaches, things like that. I've included that in your papers. So just be aware of that you'll need to access the data through Turnitin. And then also, if you are viewing this on Monday, your midterms were due last night, so I think most of those are automatically graded, so you should see your score instantaneously. That said, there was a mistake on there, and it was my fault, obviously. So there was a question, I won't be specific now in case there's anyone who hasn't done the midterm yet and you're going to turn it in late, but basically I will accept one of two different answers. I should have phrased the answer input slightly differently than it was, and so I got emails from several of you saying, "Hey, this doesn't look right," and you're right, it wasn't right. So that was my mistake. You don't have to worry about losing points, because if I make an error, that's on me. So you'll see that you should get credit for that question if you didn't know how to answer it, because obviously it was phrased wrong. So that's another bit of announcement. And then finally, this week we'll be getting into spatial statistics. This is really the first week where we dive into spatial statistics. We're going to learn a few different spatial statistical methods in GIS. We will use tools, obviously. We will kind of get to the underlying meaning behind these tools and how they apply to geography. And so without further ado, we will move on to week 9. Okay, so this week's lecture is Patterns and Clustering Part 1. Your tutorial is, let me do this a little bit backwards. Your lab is actually coming from a textbook that you do not have. Well, presumably you might, but it's not an assigned text for the class. It is GIS Tutorial Workbook 2. And so I've scanned the assignment and I have posted it on Canvas. And in addition to that, I also have, I'll pull this here on my screen, I also have some supplemental instructions. So this textbook here that you can probably see in the bottom of your screen is designed for ArcMap. Obviously, we are only using ArcGIS Pro in class, and so I have a few steps here that sort of translate it from ArcMap to ArcGIS Pro. First and foremost, I've taken the data for the textbook and zipped it into a map package, which is this .mpk. So you're going to be importing a map package into ArcGIS Pro. It's real simple. I'll walk you through it when we get in the tutorial video. You'll see how to do that. You basically import the ArcMap document into Pro, and then there are a few other steps that you just need to follow here. It's not too long. This is 2 pages long, and it's because there are two different labs. So one is tutorial 8.1 and one is tutorial 8.2. And don't get too confused. The lab itself is called tutorial 1, tutorial 2. I know I use the term tutorial to represent my little walkthroughs for you. And I am actually going to do tutorial 8.1 with you, and you'll do 8.2 on your own. But at the end of the day, you'll have 2 different maps that you'll be turning in, and they come from the actual map package, the layouts that you're going to pull out the spatial statistics, and then you will input some text onto the map layout, export that to PDF, and you'll upload those 2 PDFs to Canvas. Okay, so if you have any questions, just let me know. Send me an email or post on the message board, but it's a little bit different. So you'll have the lab will be a PDF document. You will also have this supplemental document, and beyond that, it should be straightforward. The good news is that this week's lab is actually relatively short. This week and next week are pretty short, and that was by design, because here we are on the halfway point, or past the halfway point of the semester, and so I want students to be able to spend more time on their map projects, and so it's a fairly short lab. I got through it in about 20 minutes walking through myself, so it shouldn't take you a whole lot longer than that. But just be aware of that. Shorter lab, longer tutorial this week, unfortunately, because we have to get into a lot of these spatial statistical concepts. But that's right, that's neither here nor there. I'm sure you enjoyed listening to my nasally voice this week. So, all right, so back to this lecture. Okay, so upon completion of this lecture and lab, you should understand why and how to identify geographic patterns, understand different methods for identifying geographic patterns, and understand specific GIS tools for finding spatial statistics. So, why identify geographic patterns? Why do we even do it at all? So, any distribution of features or attribute values within a defined area will create a geographic pattern. We've spent this semester so far looking at geographic patterns of features, right? So we've looked at census data, how various attribute data, display on the landscape, how some neighborhoods are poorer than others, some have a higher need for housing than others. Geographic patterns range from completely clustered to completely dispersed. So far we haven't looked at clustering. We've only looked at the data as it exists on the landscape, and we haven't asked any questions like, why is it that certain neighborhoods in Orange County tend to be poorer than maybe the county median? Conversely, why is it that some neighborhoods tend to be wealthier than the county median? And beyond that, we haven't asked the question, why is it that 10 or 20 blocks, census blocks or block groups might have a similar income level, but those income levels are different than the county average. So essentially, why is it that wealthy neighborhoods cluster together, and why is it that poor neighborhoods cluster together? Those are the questions that we're going to try to answer through spatial statistics. So a pattern that falls at the point between clustered and dispersed is considered random. So generally speaking, we might look at a data set and it might look random visually to the eye, but once you run a few tests, a few spatial statistical tests, you might find that actually the data are more clustered or more dispersed than random. So in this graph here, you see clustered on the right, the features tend to fall into little clumps, little groups. And on the left, we see that they're fairly spaced out. Okay, so if every feature is equally far apart, we call that perfectly dispersed. And if they are all in groups together, we call that clustered. And if it looks like it's a little mix of both, then it's just a random distribution. You can kind of visualize those in these sort of proofs of concept. So on the left-hand side, we have completely dispersed. All the features are equally spaced apart. And on the right, we have completely clustered. All features fall within some defined cluster. We don't have any stragglers. Everyone is in a group. And here's just kind of a couple of funny maps. So if features were randomly distributed on the landscape, we might see something like this, where the US population, instead of having population centers clustered together, which is the case, we see Southern California, the Bay Area, the Pacific Northwest, obviously the Northeast Seaboard, Florida, Chicago. We see these large clusters of population. And it's not randomly generated. It's not just by chance. People cluster in areas for a lot of reasons, but primarily for economic purposes, sometimes for cultural purposes, sometimes for ethnic purposes. And so if in some strange world everybody was just randomly distributed across the United States, you would have a map like this. So some geographer was being silly, and they essentially mixed up every county and just gave them random values, essentially. So that's what you have here. There's no rhyme or reason. We see just as similarly randomly distributed populations in Montana as we do in Southern California or near New York. Okay, and here's an even funnier concept. An elevation map. So we tend to think about clustering in terms of maybe socioeconomic data like I've talked about, or perhaps racial groups, something like that. But it also happens on the natural landscape as well. And this is a concept that may not necessarily be that intuitive at first, but then when you think about it, it's like, oh yeah, that's right. So for example, mountains cluster together in what? In mountain ranges, right? Big patches of sand cluster together in deserts. Lakes tend to cluster together in wetter, flatter areas. Okay, so even on the landscape, we see some sort of clustering by physical features. And so in this sort of bizarro world where every landscape type is randomly distributed, you have a map like this where it sort of looks like static on a TV screen, but every little blip here might be a mountain or a desert or a grassland or something like that. So obviously a counterfactual. So understanding patterns in data is useful for gaining an understanding of geographic phenomena, like finding out why are things where they are. Like why is it that wealthier people might live on the coasts and perhaps less wealthy people might live in the South, or why is it that in this case here we see um, uh, mortality rates? Why is it that people down here in the South or in Appalachia tend to have shorter lives than people on the West Coast or in the Northeast? Why is that? Well, it's a question worth asking. You're looking into the data. Understanding patterns in data is also useful for monitoring current conditions on the ground, like wildfires, things like that. Tracking changes over time, like perhaps sea level rise or desertification, and then comparing patterns. So in this case here, we've got child poverty on the left, and we have mortality on the right. And if you look at these, you tend to see there is some sort of correlation, right? Some fairly strong correlation, actually. Through Appalachia, we see a high mortality rate and high child poverty. Through the South, Mississippi, Louisiana, Alabama, we see high mortality, high child poverty. It's not a perfect correlation. New Mexico, we see high child poverty, but not necessarily the high mortality. But right up here through South Dakota, high mortality, high child poverty. So there is a fairly strong correlation, but it's not perfect. So why identify geographic patterns? For understanding patterns in data is useful for gaining an understanding of the spatial distribution of geographic phenomena. Examples of this might be what features tend to be located where, and why do we see, this is an example, why do we see a higher concentration of coniferous trees in upper North American latitudes and tropical and subtropical trees in lower latitudes? Why is it that these different vegetation types tend to cluster together at various latitudes? Well, you probably know the answer. It's colder in the north, and coniferous pine needle trees tend to thrive in colder climates, and tropical and subtropical plants tend to thrive in warmer, hotter climates, right? So that's why we see palm trees in Southern California and Florida. We see, viney trees in wetter climates. Mangoes grow in, Mexico and Central America. They don't grow in Canada, right? But conversely, pine trees grow all across the northern latitudes of Canada and North America, but you're not going to see a pine tree in Costa Rica, for example. Why identify geographic patterns? Understanding patterns are useful for monitoring current conditions. For example, where are the current highest rates of COVID-19 in the United States? Well, this map is accurate as of, I want to say it was this past Thursday. Okay, so you can see that there are high concentrations of COVID-19 rates in the South again, and in the Dakotas. Obviously, California is, we're sort of leveling off, but we're certainly not out of the woods yet. What are current water temperatures in the Western Atlantic Ocean? So monitoring current conditions. Why might we want to monitor water temperatures in the Western Atlantic? Well, it's hurricane season, right? Warm ocean temperatures tend to sort of nurture the growth of tropical storms, which can become hurricanes. So it's good to keep a monitor of those, and you can track those patterns with GIS. Speaking of, tracking changes over time. So, example, why is the Eastern Pacific Ocean colder than usual for this time of year? Well, it's a La Nina year. Indeed, it is. And so you can see this is actually an ocean temperature anomaly map showing you that blue just means colder than average, and red means warmer than average. Other question, is mountain vegetation drier than usual this time of year? There's a typo there. Why might we want to know if mountain vegetation is drier than usual this year? Well, you live in Southern California, and so you know that dry vegetation in the mountains in October means fire season. So something you want to track over time. So using statistics to identify patterns. Using statistics to identify patterns, in addition to measuring features and values on a map, they may also be measured using statistics, which is what you'll be doing in today's lab. So we've spent a lot of time looking at data on maps, essentially using our eyes. but there are other ways to measure statistics as well, measure values rather, and that's through math, right? And really, when it comes down to it, GIS is just it's geometry. It is math, right? But we don't tend to think of it that way. We tend to think about it as geometric features, which again are collections of XY coordinates, which again it's a form of math, right? Statistics allow you to discover if features are clustered, dispersed, or random, as we've talked about, and you can compare patterns between different data sets and compare changes over time. When using statistics to measure patterns, the observed distribution of features is compared with a hypothetical random distribution of the same number of features over time. The deviation, this is the key thing, the deviation between the observed and the random distribution indicates whether the observed data are clustered or dispersed. So in some hypothetical random distribution, you might see a fairly evenly distributed set of features, right? Because it's random. There's no forces pulling features or pushing features into one group or another, either clumped together or dispersed. So if we see something that deviates from what would be expected in a random distribution, then that tells us that it's something significant. It's no longer just random. It might be that features are clustered together or are dispersed. So the process of measuring a pattern by comparing an observed and a random distribution is based on the scientific method. The scientific method basically state a null hypothesis, then set out to determine whether to reject it or not with some level of confidence. That's just essentially the basic scientific method. So we ask a question, we do some background research, we construct a hypothesis, we test the hypothesis by doing experimentation, we analyze the results, and then we draw conclusions, okay? And so the null hypothesis is a statement that essentially outlines an expected outcome when there's no pattern, no relationship, no systematic cause or process at work. And so essentially you can think of the null hypothesis as the state of being in a random situation without any sort of animating factors, no causal factors at play, okay? So any observed differences are the result of random chance in this null hypothesis. The null hypothesis for a spatial pattern is typically that the features are randomly distributed. Think back to the maps I showed earlier, like a map of the US where all the landscape types are randomly distributed, right? So in that case, it's obviously unrealistic, but again, it's a hypothetical scenario. So if you could picture a country where all the geographic or physical features were randomly distributed, that would be the random distribution. But we know that mountains cluster together, lakes cluster together in some places. The Great Plains are a giant region. Deserts cluster together, right? So we know that the distribution of features on North America are not randomly distributed. They follow some sort of rhyme and reason, and that's related to lots of things, plate tectonics and, the prevailing winds and precipitation patterns and all of that, right? So there's some sort of causal factor that has formed the geomorphology of planet Earth, right? So the null hypothesis for a spatial pattern is typically that the features are randomly distributed across a study area. The results of an analysis can be tested to calculate the probability that a pattern isn't simply due to chance. And we call these significance tests. So significance tests help determine whether the null hypothesis should be accepted or rejected by giving a probability that what a statistic is telling you is true. So a significance test will tell you that there is a 99% chance that these results are probable, okay, or that they are significant, rather. Conversely, you might have a lower significance, so that you might see some sort of clustering or dispersion, but the level of confidence is fairly low. In that case, you have a lower p-value, and so you would say, well, we have to kind of take this data with a grain of salt, right? Calculating this probability is important for having a high level of confidence in decisions made as a result of findings. So if there's a low level of confidence, then it's likely that you would not want to take action based off of those statistics. So what are the benefits of measuring patterns with statistics? Well, using statistics to measure patterns is more accurate than identifying patterns visually on a map. Thus far, we have primarily only measured patterns visually. So as I said before, we haven't been paying much attention to clusters and dispersion. So on a choropleth map, the specific classification method, the number of classes, and the class ranges can all affect whether a pattern is visible. So there may have been patterns of clustering and dispersion in past maps that we've looked at, but those patterns are often washed out by various classification methods. So maybe there are too few classes or too many classes. Maybe natural breaks is not always the best one. Maybe quintiles or some sort of geometric classification method would be better. And class ranges can wash it out as well. So having the right combination of those helps those patterns show through. But since statistical tools use the underlying data values for each feature, identifying patterns does not have to depend on how values are classified and displayed. So that's why we use these various tools in the GIS they don't rely on the actual geometry as much as they rely on the underlying data values in the attribute table. So if point features are stacked together on top of a map, it's difficult to visually discern density, for example. So you might have 10 different features at one single location. We'll say like robberies, for example. We'll say that there's some street corner where people get robbed a lot, and so like you could have 20 different robberies at one single street corner. Well, if you geocode that data, they all happen to be at the same point. And so when it comes to density on a map, you might be able to tell that it's a higher density, but you don't know necessarily that they're all clustered together in one single location. But using statistics to measure the distribution and the pattern of features avoids the problem, since each individual point is counted in the calculation. Measuring the pattern of feature locations. So the patterns formed by the distribution of features can be measured several different ways, or several different methods for this. I'm going to touch on just three. The quadrat analysis. This allows you to overlay areas of equal size and then find out the distribution within the area. Nearest neighbor index, which calculates the average distance between features. And you're actually going to use nearest neighbor index in this week's lab. And finally, k-function. K-function is for counting the number of features within a defined distance. So we'll go into each of these. So measuring patterns with the quadrat analysis. The GIS, what it does is it overlays areas of equal size on the study area and counts the number of features in each quadrant. So you can kind of think about this if you've spent any time in, like, I will say, field school. If you have any background in archaeology or cultural anthropology or anything like that, you'll notice that oftentimes in field school or in the field where you're doing a study, anthropologists or geologists will lay out a grid with stakes and string, essentially. So, you just take stakes, you put them in the ground at equal intervals or equal distances, put a string connecting them, and you end up making various quadrants or squares. And so what you can do, let's say if you work in cultural resource management, you might be able to count the number of, we'll say, arrowheads or some sort of artifact within an area. And if you find that there are 10 artifacts in this one quadrant, and maybe 8 to the north of that one, 6 to the east of that one, and then 3, and then 2, and then 1, you know that they happen to be clustered in this one area. And the farther you get from that one quadrant, the distribution tends to get more dispersed and it's less significance. Okay, so GIS overlays these quadrants, in this case a digital form, over the data set where each of those points is located, and then it counts the number of features in each quadrant. But then also what it does is it counts what would be expected in a hypothetical random distribution. So if you took the same number of features in the same total area, it would randomly distribute them. And so instead of finding maybe one quadrant with 10 or 8 artifacts, you would expect to find 2 or 3, okay, in a randomly distributed data set. And then what it does is it compares the two. And if fewer areas than expected contain most of the features, and more areas than expected contain few or no features, excuse me, it's a typo, few or no features, the features form a clustered pattern. So just like the scenario I just explained, you'd see it on the GIS looking something like this, where we see a high clustering right in this area and a low occurrence of features out here to the right. Quadrat size will affect whether any patterns are identifiable. So quadrats that are too large might end up showing too high concentration in one area, but you lose the precision. So quadrats should be large enough to capture the patterns, but not so large that the patterns are obscured. Okay. Quadrat analysis is useful when there is no direct interaction between the features. For example, when analyzing the distribution of plant species or condor sightings, or in the example I just cited, arrowheads or artifacts where they're not necessarily related to one another. It does not take into account proximity of features or their relative arrangement. So when it comes to quadrat analysis, all you end up seeing is the output, finding out that, and so there's a high distribution here, but where they're at and the relative location to one another is not accounted for. Nearest neighbor index. This is a slightly different approach. In this case here, the GIS finds the distance between each feature and its closest neighbor, then calculates the average of these distances. Okay, so it does that for every single individual feature. It takes the feature location and then its nearest neighbor. So let's say that you found one artifact. We'll say it's a bowl or a shard of a bowl, and then its nearest neighbor happens to be 3 feet away, and it is an arrowhead. And so its nearest neighbor is 3 feet. Then it goes to that arrowhead, and it looks for its nearest neighbor. And then it goes to something else that's been found. We'll say it's a jar. Looks for its nearest neighbor, and to that jar, the nearest neighbor is an article of clothing, and it's 10 feet away. And so it takes all the various features and it finds its closest neighbor, and then adds all those differences or distances together, averages them out. Okay. So the nearest neighbor index measures how similar the mean distance is to the expected, once again, the expected mean distance for a hypothetical random distribution. Okay. The index is the ratio of the observed distance divided by the expected distance. To calculate the index, the GIS subtracts the expected mean distance from the observed mean distance. Formulas there. That's distance is equal to the mean distance of the observed minus the mean distance of the expected. If the observed and expected means are equal, then the difference is 0 and the observed distribution is random. Okay, so if they're the same, the expected and the observed are the same, it's random distribution. If the expected mean is greater than the observed mean, then the difference is a negative number and the observed distribution is clustered. If the expected mean is less than the observed, then the difference is greater than 0 and the observed difference is dispersed. Excuse me, observed distribution is dispersed. Lastly, we're going to talk about k-function. So in this case, the GIS counts the number of neighboring features within a given distance of each feature, then sums the values. So in this case here, you can look at the graphic. Each individual feature will be essentially focused upon, and then from there we will count, or it will count the number of features within a given radius. Okay. So if the number of features found within the distance is greater than the random distribution, then the observed distribution is clustered. K refers to the distance bands that are established around each feature. And so these can be defined. So maybe it's from each feature we look at a 10-foot radius, and then perhaps a 20-foot radius, and then a 30-foot radius. And each one of these might show a different level of clustering or dispersion. To calculate the case statistic, the GIS finds the distance between each point, then for each individual point counts the number of surrounding points within a defined distance. And as I said, you could change those, change that defined distance. Then the GIS draws a circle around a point in the set using the radius equal to the first distance, counts the number of points found within the circle, then moves to the next point, then the next point, and so on and so forth until it has summed points within the radius of each individual point. So just so for your own reference here, we have the 3 different measurement methods, the tool that you would use, what the method is, the tool, the benefits, and the trade-offs. I like to display it this way, and also I've found that the book tends to kind of summarize various tools this way. So I think it's helpful, especially for students as they're developing their research projects. All right, so we will leave it at that for this week, and then we will carry on later next week, and we will get into measuring the spatial patterns of features but we will leave it at this for this week. Okay. All right, so go ahead and move on to the tutorial at your convenience. And until next week, have a good one. Bye-bye.